So I now want to talk about term-by-term differentiation of Fourier series. So I have the theorem written over here. So don't read this part of the board yet. Let's just look at the left-hand side. And let's try to talk about why there is a problem with term-by-term differentiation of Fourier series. So e to the x, let's think about the cosine series for e to the x. I've got e to the x is equal to 1/2 a naught, and we'll look at just from 0 to pi. So this is k equals 1 to infinity ak cosine kx. Now the theorem that we looked at before says that the Fourier cosine series will converge to e to the x on all points of 0 to L, including 0 and L. Okay, but let's think about doing term-by-term differentiation to try to compute what the coefficients are. So we know there's an integral formula, but let's try to compute them in a different way using the fact that the derivatives of e to the x are all equal to e to the x and using term-by-term differentiation. So the derivative of e to the x is e to the x. So now I'm going to do term-by-term differentiation over here, and what I get is the sum k equals 1 to infinity minus k ak sine kx. Okay, so far so good, perhaps, as long as we're allowed to do term-by-term differentiation. The hint is we're not, and we're going to have some weird problem here. So continuing this, if I take another derivative, again, since e to the x is equal to e to the x, this is going to be the sum k equals 1 to infinity minus k squared ak cosine kx. Now this is allegedly a Fourier series for e to the x. This is allegedly a Fourier series for e to the x. But I've got cosine kx in both functions. So the only way this series can equal to this series is if minus k squared ak is equal to ak. In other words, the corresponding coefficients have to be equal to each other. Well, this is clearly not true. Well, the only way this is true is if ak is equal to 0. In which case, this just says e to the x is equal to 0, which is not true. The other possibility would be that e to the x is orthogonal to all of the cosine of kx's, but we know that's not true just by doing the computation. But our theorem says that this should equal to e to the x. But if ak's are all equal to 0, there's no way this can be true. Okay, so what's the problem? So the problem turns out that this term-by-term differentiation is okay. We just haven't justified it by stating a theorem. This is where things are not okay. Okay, so the theorem, we actually have a problem differentiating this particular sine series term-by-term. Okay, so I want to state a theorem about the term-by-term differentiation of Fourier series, but I'm not going to say it for cosine series or sine series. I'm going to state it for the full Fourier series, and just from minus pi to pi. So remember, if f is defined, on the interval minus pi to pi, the full Fourier series is going to be 1/2 a0 plus the sum k equals 1 to infinity ak cosine kx plus bk sine kx, where the ak's are given by 1 over pi times the integral from minus pi to pi f of y cosine ky dy. And the bk coefficients are given by 1 over pi times the integral from minus pi to pi f of y sine ky dy. Okay, now I can state the theorem over here. So let f be continuous on minus pi to pi. Okay, so continuous is pretty clear. We know what continuous means. And piecewise differentiable on minus pi to pi. Okay, so what does piecewise differentiable mean? It means that its derivative might not exist at every point, but it exists piecewise. So the primary example, or kind of the most famous example, would be the absolute value function. It's continuous from minus pi to pi, but its derivative doesn't exist at 0. But it exists from minus pi to 0, and it exists from 0 to pi, so we would say that f is piecewise differentiable. Okay, and if f of pi is equal to f of minus pi, then the Fourier coefficients for f prime, which are going to be these capital letters, are given by the following formulas. So I'm going to erase this here for now. So what would we want to be true? If I do term by term differentiation, if this is equal to f of x, then doing term by term differentiation, I'd get the following: the sum k equals 1 to infinity minus k ak sine kx plus k bk cosine kx. I'm just doing term by term differentiation. And what the theorem says is that if f satisfies this, and big AK and big BK are the full Fourier coefficients for f prime, then they are exactly what you want them to be. So the big AKs are the coefficient on cosine kx, and we're saying that these are indeed equal to kbk, and these are the bk's, these are the coefficients on sine of kx, and these are indeed equal to minus k ak. Okay, now let's be clear and careful about what this first part says. This first part says that it gives us a formula for the Fourier coefficients for f prime in terms of the Fourier coefficients for f. So it gives us a formula for the Fourier coefficients of f prime in terms of the Fourier coefficients of f. But it does not say that the full Fourier series for f prime converges to f prime. That's what the second part says. The second part says if, in addition to everything that we have up here, f prime is piecewise C1, so this means that not only is it piecewise differentiable, but that derivative is piecewise continuous. Okay, now practically speaking, in practice, there's not a lot of, meaning functions that you're likely to see, there's not a lot of functions that satisfy this that don't satisfy that. If f is piecewise continuous, then the full Fourier series for f prime, I don't know why I have a phi there, for f prime converges to f prime of x plus 0 plus f prime of x minus 0 over 2. In other words, the average, if f prime is continuous, this is just equal to f prime of x. If it's discontinuous, it converges to the average of the jumps. Okay, and this is, given the theorem that we looked at on Wednesday, this is about the best that we can do. Okay, so let's look at an example. Let's catch the full Fourier series for a specific example. So let's look, or the derivative, the full Fourier series for the derivative. So let's say this is minus pi, this is pi. We have this function here. The function on the right-hand side is going to be 1 minus x minus pi over 2 squared, and then we're going to have a function here. This is minus pi over 2, and the slope here is going to be 1, and the slope here is going to be minus 1. Okay, and you can figure out what the formula should be. Well, this is just going to be minus x. Okay, so let's sketch the full Fourier series then for the derivative. Okay, so let's look on the left-hand side. Okay, on the left-hand side, I know the derivative is going to be equal to 1 here. So from minus pi to pi over 2, it'll be 1. From minus pi over 2 to 0, it'll be equal to minus 1. Okay, now the derivative of this function is equal to minus 2 times x minus pi over 2. Okay, so this, let's say this is pi over 2. This is going to be a line with slope minus 2, and the y-intercept is going to be equal to pi. So if I do this a little more to scale, this is pi, this is 1, so it's going to be something roughly like this. Okay, and open there because there's a discontinuity in the derivative right there. Okay, so where will the Fourier series converge? Let me make this a little more to scale and make this up at minus like this. Okay, so where the derivative is continuous, the Fourier series will converge there. Here's a jump discontinuity. It's 1 here, it's minus 1 here. And the average is going to be equal to 0. So that's where the full Fourier series will converge. Let me fill that in. Okay, now here and here we have pi plus minus 1. Okay, so 3.14 minus 1, that's 2.14. We divide by 2, we get something a little bit bigger than 1. So something like this. So this is going to be where the full Fourier series for this function, the full Fourier series for the derivative of this function will converge. And it's not so important. Well, anyways, never mind. Okay, this is where the full Fourier series will converge. Okay, so one last thing that I want to mention, just to remind ourselves, why do we care about the convergence of, why do we care about term-by-term differentiation? Well, let me just bring one example. So remember, let's look at the diffusion equation, or the heat equation if you wish. This is the t derivative of u is equal to the double x derivative of u. And we'll look at u of 0t is equal to u of pi t, and that's equal to 0. And then we'll give it an initial condition, u of x0 will be the sum, k equals 1 to infinity, bk sine kx. Okay, then we said that the solution, or at least our claim, is that the solution is going to be the sum, k equals 1 to infinity, bk e to the minus k squared t sine kx. Okay, now to show that this satisfies this equation, we have to do a term-by-term differentiation in the t variable and the x variable. Now, because this is decaying so quickly, doing a term-by-term differentiation in the t variable isn't a problem. The problem is potentially doing a term-by-term differentiation in the x variable. Now, let's look at something here. We only have information about u from 0 to pi. But the theorem that we've stated over here is about a series going from minus pi to pi. So how can we connect these two things together? So let's begin. In other words, I need something about term-by-term differentiation for a series. I need something about a term-by-term differentiation for a sine series from 0 to pi, but I only have a theorem about term-by-term differentiation for a full Fourier series from minus pi to pi. So how can I do this? Well, the first thing that I want to point out over here is that for this function, by definitions of here, the Fourier coefficients, the Fourier cosine coefficients are equal to 0. Okay, and what we're having to think about here is we're fixing a value of t. So it's like for every value of t, we get a different function. And like these are going to be the Fourier coefficients for that fixed value of t. But the AKs are equal to 0 because there's no cosine terms. But the BKs are equal to, the Fourier coefficients for this function for a fixed value of t are going to be equal to bk e to the minus k squared t. That's just because that's what we have here. And this is equal to 2 over pi times the integral from 0 to pi of u of xt sine ky dy. Okay, so let's say this is pi. And let's say I've got my function from 0 to pi. I don't know, what do I know about u? So I'm going to graph u of xt for a fixed value of t. What do I know about u? Not a lot, but it's going to look something like this. Meaning it's 0 here and 0 here. And so now what I'm going to do is I'm going to take the odd periodic extension. I'm going to look at not the periodic extension so much, but the odd extension over here to minus pi. And it's going to look something roughly, I'm going to get it wrong, but it's going to look something roughly like this. Okay, this is an odd function. Now let me do that. So I'm going to go like this, and then like this. something like that. Okay, so this is the odd extension of that function. Okay, so notice this function satisfies, it is continuous from minus pi to pi. It's piecewise differentiable. We'll just assume that it's piecewise differentiable because it's differentiable over here, and so that means it has to be differentiable over here. The only case where there could be a problem is at the origin, but that's okay. It'd still be piecewise differentiable. And the derivative is continuous at each spot. And f of minus pi is equal to f of pi. They're both equal to 0. Okay, so then what this tells us is that we can do term-by-term differentiation of this function on the full series. Okay, so how do we translate this to just something about, how do we translate this to being something about the sine series from 0 to pi? Well, the first thing to think of, if I look at the cosine coefficients for this function, the cosine coefficients, okay, so I'm going to say u tilde is the extension. So u tilde is the extension. The Fourier coefficients are given by the integral from minus pi to pi, 1 over pi. We're going to have u tilde of yt cosine of ky dy. Okay, so what's going to happen here? U tilde is an odd function, cosine is an even function. So overall, their product is an odd function. We're integrating from minus pi to pi. So this integral is equal to 0. Okay, so the full Fourier coefficients are going to be equal to 0. The full Fourier cosine coefficients are going to be equal to 0. Okay, what about the sine coefficients? So if I look at the full sine coefficients, so if I look at the full Fourier sine coefficients, what can I do here? Well, u tilde is odd, because I took the odd extension. Sine is odd, so their product is even. I'm integrating from minus pi to pi. Well, if I'm integrating an even function over these symmetric bounds, I can replace this with a 0 and that 1 with a 2, which is exactly what we have down here. So, in other words, if I take the odd extension of my function, the full Fourier sine coefficients are the exact same as the sine coefficients just from looking at 0 to pi. So what the theorem says is that I can term by term differentiate the full Fourier series. That turns out to be the exact same thing as the sine series from 0 to pi, except now it's actually true from minus pi to pi. So what the theorem says is not only can I differentiate this series term by term from 0 to pi, I can actually differentiate it term by term from minus pi to pi. In particular, the term by term differentiation is valid from 0 to pi. Okay, so now here's a challenge problem that you guys can do on your own, and maybe talk about in the discussion forum if you want. What about if I look at the Neumann boundary conditions? I'm going to have an x derivative here and an x derivative here. Now I no longer know that my function is going to be equal to 0 here and 0 here. It could be equal to something like that. Okay, so now how can I apply this theorem? Because I no longer have that it's equal to 0 there and 0 there. Okay, and the hint is instead of taking, and now the other change is that this is going to be cosine and then plus 1/2 a0. So that's the other change that we're going to have to make. So do a similar reasoning to show that we can do term by term differentiation. This would also be cosine. That we can do term by term differentiation. Instead of taking the odd extension, think about the extension that you'll want to take to do similar computations. I know this is a lot, but doing that exercise will sort of really solidify your understanding here. Okay, that's it for today.